In our previous lessons, we've been working on solving systems of linear equations graphically and algebraically by substitution. We want to see if there's another way that we could solve some systems algebraically where it doesn't always necessarily mean that we have to take one of our equations and solve for either an x and y and substitute into the other. So here we have these two equations, x plus 5y equals 28 and negative x minus 2y equals negative 13. Typically, in the past, we've looked at the equations, and our first one, we could make an x equals fairly easily by subtracting 5y from each side and substitute in, distribute, solve for y, and then we could substitute that answer in for x and solve and find the value for x. But is there another way that we could solve for one of our variables without having to make an x equals or y equals? Well, as I look at these two equations, I did have a single x here, and if I notice the second equation, I have a negative 1x there. So what if I just added the equations together to eliminate the variable x, because a positive 1x and a negative 1x is equivalent to 0. In doing so, when I add the y's together, a positive 5y and a negative 2y would give me 3y. And if I add my constants, 28 and negative 13, that gives me 15. So now I have an equation, 3y equals 15. I could easily get y alone by dividing both sides by 3. So 3y divided by 3 would just be y, and 15 divided by 3 is equal to 5. So here I have the value for y. Well, if we're doing our system, we not only need to know the value for y, we also have to know the value for x, because remember, these are two lines that we want to see if they intersect at one location, and what is that location going to be. So that's a coordinate, that location. So if I take that value for y and substitute into one of the equations, like the first one, I should be able to solve for x. Well, 5 times 5 is 25, so I have x plus 25 equals 28. By subtracting 25 by each side, I'll have x equals 3. Therefore, it appears my solution is 3, 5. And again, just like we did before, we want to verify that this is the correct solution. So we're going to substitute 3 in for x for both equations and 5 in for y for both equations to make sure that they really are balanced. So my first equation, I'll have 3 plus 25. That does give me 28, so we're okay on that one. And our second equation, we'll have negative 3 minus 10. That will give me a negative 13, so my solution does check out. So solving by elimination, eliminating one of the variables, is another efficient way of solving a system algebraically, as opposed to always having to make an x equals or a y equals. So let's take a look at another system. Here we have 3x plus 2y equals 10, and 3x plus 2y equals 2. And so again, we want to try eliminating one of the variables so we can solve for the other. Well, we don't have a single x or a single y, so it would be a little bit time consuming to make an x equals or y equals. But if I look at these two systems, again, I'm noticing I have the same amount here for my x, 3x, and I have the same amount here for 3x. Well, if one of them was a negative and I added it to the positive, that would make a 0. So perhaps if I multiplied one equation by a negative 1, I could add them then together and eliminate one of my variables. So why don't I take the second equation and multiply everything there by negative 1, and then I can add the two equations together. So I would have my first equation untouched, 3x plus 2y equals 10, and my second equation is now negative 3x minus 2y equals negative 2. Well, when I add them together, a positive 3x and a negative 3x would give me no x's, so 0. And a positive 2y and a negative 2y, that will give me 0. And a 10 and a negative 2 would give me 8. So here I'm left with 0 equals 8. Well, we know that 0 does not equal 8. That's not true. Since that's false, that means that there's no solution. And we know algebraically when no solution occurs, that's telling us, hey, we have parallel lines. They will not cross. Let's take a look at another system. 5x plus 6y equals negative 11, and 3x plus y equals negative 4. Again, we want to be able to solve the system so we can figure out what value for x and y will make both of those true. So again, as I look at the system, I'm looking to see what I'm working with. And I can see in the second equation here, I have a single y. So we could solve this by substitution, by getting the y alone, substituting it into the first equation, solving for the value of x, get that value for x, substitute in, and then I could find my value for y. But also talking about eliminating a variable, this is a positive 1x, sorry, positive 1y. And here we have a 6y. If I had a negative 6y, I could make a 0 with my positive 6y, and then I could just solve for x. Well, in order to do that, I could take this second equation here and multiply everything by negative 6. So let's try that. So I would be working with, in the second equation, a negative 18x minus 6y equaling 24. Remember, I'm not changing the first equation at all. That remains 5x plus 6y equals negative 11. Well, now if I add my two equations together, a positive 5x and a negative 18x will give me a negative 13x. A positive 6y and a negative 6y would give me 0y, so 0. A negative 11 and a positive 24 would give me 13. So here I'm able to solve for x fairly easily. These are being multiplied together, so to undo that, I could divide each side by negative 13. So I'd have x equals a negative 1. Now that I have the value for x, I can substitute it into either of my equations and solve for y. So we just need to pick an equation to do so. Well, let's go with the first equation. 5x plus 6y equals negative 11. If I substitute negative 1 in for in for x, I would have negative 5 plus 6y equals negative 11. We just undo the equation to get y alone, so that means I'd have to add 5 to each side. So 6y equals negative 6. Then to get y alone, we divide each side by 6, so y equals negative 1. So it appears our solution would be at negative 1, negative 1. Well, the only way we could verify that this is true is take both of the values for x and y and substitute into both equations and make sure that they're true. So let's do that. So our first equation, by substituting our values for x and y, we'd have negative 5 and a negative 6. That would give me a negative 11. Our second equation, we would have a negative 3 and a negative 1. That would give me a negative 4. Therefore, we verify that the solution, negative 1, is true for our system. Let's have you try another one. Here we have negative 3x plus 5y equals 6, and 6x minus 10y equals negative 12. Again, we want to solve the system, seeing if we can eliminate a variable. So comparing the two equations, I have a negative 3x here and a positive 6x here. If this was a negative 6x, that would make a 0 with my x's, and I could solve for y fairly easily. So let's take that top equation and multiply it by 2. So that equation would then transform into negative 6x plus 10y equals 12. And I'll keep the second equation as is. When I add them together, we'll have 0 from the x's. A positive 10y and a negative 10y would be 0 as well, and 12 and negative 12 is also 0. Well, 0 does equal 0. That's a true statement. Therefore, this is telling us that we have infinitely many solutions. That means those equations represented the same line. Let's try another. Here's our system. 4x plus 5y equals 35, and negative 3x plus 2y equals negative 9. We'd like to solve the system and figure what value for x and y would make both of them true. Again, comparing the equations, we can see we don't have any single x's and y's, so substitution would not be a good idea, or it would take us a lot of time to get the x or y alone, so let's skip that fact. And I'm looking to see what I'm working with, and I have a positive 4x and a negative 3x. Well, 4 and 3, they have a common multiple of 12. So if I had a positive 12 here and a negative 12 there, that would make a 0. So I can multiply the first equation by 3, so I'd get that positive 12x, and I can multiply the second equation by 4, and I'd have my negative 12x. Then I could add the two equations together to make that 0. So here's what would result. My first equation would be 12x plus 15y equals a positive 105. The second equation, I have negative 12x plus 8y equals negative 36. So by adding the two equations together, I'll make this 0 with the x's, which is what I wanted. 15y and 8y would give me 27y, and a positive 105 and a negative 36 gives me 69. To get y alone, we could divide both sides by 23, so y equals 3. Now that I know the value for y, I could take it and substitute it into one of my equations and solve for x. So let's pick one equation. Let's go with the first one. And if I substitute y into that equation, I would have 4x plus 15 equals 35. We just undo the equation to solve for x, so I'd subtract 15 from each side. So 4x equals 20. Then I could divide both sides by 4 to get x alone, so x equals 5. So it appears that our solution would be 5, 3. We have to verify that this is correct by substituting 5 and 3 in for x and y into both equations and make sure that it's balanced. So our first equation, 4 times 5 plus 5 times 3, 20 plus 15 gives us back our 35. So that's okay. Now checking our second equation, we would have negative 15 plus 6, and that gives us back our negative 9. So we verify that this is the location where both lines will meet. Let's try another. Here's our scenario. Zane has 63 baseball and hockey cards. He knows that he has 3 times the number of baseball cards minus 4 times the number of hockey cards is 126. We need to figure out how many of each kind of card he owns. Well, when given a scenario, I typically remind you to underline what you know and circle what you want to know. We have to be able to write a system to represent what is going on with our scenario. So what do we know? We know that Zane has 63 baseball cards and hockey cards. We also know he has 3 times the number of baseball cards minus 4 times the number of hockey cards is 126. We want to know how many of each type he has. So we keep talking about 2 types of cards, baseball cards and hockey cards. Those are the 2 variables that we are working with. So I'll say B equals baseball cards and H equals hockey cards. The number of baseball cards and hockey cards is 63. So B plus H equals 63. We also know 3 times the number of baseball cards. So 3B minus 4 times the number of hockey cards, 4H, is equal to 126. So here's the system that we need to solve. So by examining what we have here, I'm trying to make a 0 with one of my variables. So I have a negative 4H and a positive H. If this was a positive 4H, I can make a 0 when I add the equations together. So let's take that first equation and multiply it by 4. In doing so, I'll have 4B plus 4H equals 252. I'm not going to change the second equation. I want to keep it as is. 3B minus 4H equals 126. Because when I add the 2 equations together, the goal was to eliminate a variable, and I'll end up eliminating H. That will give me the 0. So 7B equals 378. To get B alone, we would divide each side by 7, and B equals 54. That's the number of baseball cards that Zane has. Well, we also have to figure out the number of hockey cards, so I could take the number of baseball cards and substitute it into one of the equations. Let's use the first equation. If he has 54 baseball cards plus the number of hockey cards he has equals 63, I could undo this to find the hockey cards. By subtracting 54 from each side, we know H is 9. He has 9 hockey cards. So it appears Zane has 54 baseball cards and 9 hockey cards. Well, to verify that this really is the scenario, we would take 54 and 9 and substitute in both equations and make sure it's balanced. Well, we know 54 and 9 gives us a 63. 3 times the 54 minus 4 times 9 does give us back the 126. So we know that we have the correct number of cards in Zane's collection. So we've been talking about different ways we can solve a system of linear equations, and we've come across 3 of them. We know we can solve them by graphing, looking to see where the 2 lines intersect. They will either intersect at one point, they will intersect at infinitely many points, or they will not intersect at all. We also talked about solving a system by substitution, and it's also a way algebraically where we're locating where the lines intersect. That is when you're trying to solve for a variable, x equals or y equals, and substitute that into the other equation to find the value of the variable. So you can take that value, substitute it back into the other equation, and find the other value. Elimination is also an algebraic means of locating where the lines intersect. This way is what we're practicing today, is eliminating one of the variables by multiplying one or both of the equations by a value so that when we add the equations together, one of the variables makes a 0. So you only have the other variable to solve for, its value, and you could substitute it into one of the equations and find the other. At this point, you're going to be doing more practice with solving by elimination on your Unit 4, Day 4 homework worksheet. Always make sure you're checking and verifying that you do have the correct solution to your problem.